No, but so like they can't stop. They literally all.
I was like, he played like shit, but he commented.
Yeah.
I was like, yeah, I was like, like the first quarter. I know, 20. Well, I guess. Yeah.
LeBron.
Okay.
Okay, so let's go ahead and get started. So like I mentioned last class, we're mainly going to talk about lab 4 today. I'm going to go over the diagram and explain how the circuit works. And the lecture will probably be about 50 minutes or so, depending on how many questions there are. But then you'll have the remainder of the time. So you should have about the last 2 hours or so to work on lab 4. There is an activity, but the activity is different than the previous activity. The previous activities were, paper related. This activity is actually a demo. Okay, that I want you to demo something, and I don't think many people, if any, will be able to demo it today. So that's why, if you look over on the right side of the board, the activity of this demo, it's not due for, as long as you show me by the end of next Thursday's class. Now remember, next Thursday we have the midterm. The midterm is the first 60 minutes of class. So when you come in at 3:10, you'll start the midterm and you have 60 minutes. And then after the midterm, there's a short lecture, and then have the remainder of the time to work on whatever you need to work on. Okay. Make sure, and I mean this is true for every class, but especially for the midterm, make sure you're here on time, because if you're late, you lose that time. If you're 10 minutes late, you're only going to have 50 minutes to work on the midterm instead of 60 minutes. Okay, and I've already shown you the topics, right? Remember, there's a handout I passed out that had the policy along with the topics. So, the material you're responsible for goes from the beginning of the quarter all the way through today's class. Monday of next, or Tuesday of next week, we'll talk about sequential circuits, which have memory, but there won't be any material from Monday's class on the midterm. Okay? And if you have questions about the midterm, like at some point, maybe towards the end of the lecture today, you can ask. Okay? Oh, the other thing about the midterm is you do have to take it in your enrolled section. Okay, usually that's not a problem in a section like this, because usually nobody wants to take it earlier. But my earlier sections, they can't take it later. And then also, as I had on that handout, you're allowed to use a calculator on the midterm. But again, you got to show your work for credit. So don't punch everything into your calculator and just write down an answer, because you won't get any credit for that. Now, before I talk about this diagram for lab 4, I just want to review 2's complement numbers, along with addition of 2's complement and subtraction by addition of 2's complement, and also the validity rules. Okay, because this plays into this lab. So first thing, when you have a positive number, what is this most significant bit equal to? There, right, because we call that most significant bit the what bit? The sign bit, right? And it's been agreed upon that when that sign bit is a 0, we have a positive binary number. So what would this equal in base 10? Right, plus 3. Right, because like we talked about, if it's a positive signed binary number, you just figure out the magnitude like you would an unsigned, right? Except the sign bit doesn't have value. Okay, how about if it's a negative number? Our sign bit's what? 1. So if we have this, how would we get the value in base 10? How do you find the value if it's a negative 2's complement number? What do you have to do? You have to do something and then something. Yeah, you flip the bits, then add 1. Remember, if it's a negative 2's complement, to get the value, flip the bits, add 1. So this would be -5, correct? Everybody agree? Okay. So any questions on that? Good. All right. So also, last time we talked about that when you do sign binary addition or sign binary subtraction by addition, you always need to check to see if your answer is valid or not. And I gave you 3 rules, right? 3 validity rules. Can somebody give me one of those rules? What's one of those? Which one? Were you gonna give me one of them? Which here? Okay. Yeah, so positive plus negative is what? Right, always valid. Very good. Thank you. All right. Okay, somebody else give me another rule.
Positive plus positive must be, it might be valid if it is positive.
Well, it will be valid, yeah. If you're adding 2 positives and your result is positive, it is valid. So if positive results. Valid. Okay, and then also if you're adding 2 negatives, if you have a negative result, it's valid. Now, I also talked about how another way to determine if you have a valid result or not is that if your result is within the range for that number of bits that you have, then that's valid, right? But if you get a result that's outside the range for the number of bits you have, well, that's invalid. Okay, so that's another way. But these are the rules. Okay, the 3 validity rules. Okay. Okay, so let's do an example of addition here. So, again, this is all 2's complement. So, this is the sign bit column. So again, when you add signed binary numbers, it's the same process as you would do if they were unsigned. You just go column by column, right? So 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, a carry. Okay, so that's how we do it manually. Now, what can you say about this result? Invalid, right? Because we're adding 2 negatives and the result comes out positive. So this is invalid. Oops. Okay, also, when you get a bit that's to the left of the sign bit, what do we do with that bit? Yeah, you just throw it away, right? It doesn't have any meaning. Okay, and then again, we could convert these to -10 or to base 10, just to double check that this invalid is the right conclusion. Again, converting these to base 10 is not something you have to do, right? But I don't know. When you're first learning this, I think it's a good thing to do just to make sure you're doing it right. So if we have all 1s like this, what is this in base 10? Well, first of all, is it positive or negative? Negative, right? Because the sign bit is a 1. Yeah, this one negative. And then say it again. Well, remember, you flip the bits, that would give you 0, but then you got to do something else. Add 1, so it's -1. Yeah, if you just flip the bits, that's 1's complement. Okay, but 2's complement is flip the bits, add 1. Okay, so this is also going to be minus. Okay, but what value is this? -6. Right, because you flip the bit, 0, 1, 1, 1, that's 7, add 1, that's it. Okay, so look, we're adding -1 and -9. So can you see why it's invalid? Because -9 is not in the range of 4-bit 2's complement. Because what's the most negative value you can have with 4 bits and 2's complement? -8. Okay, so anyway, just another way to come to the same conclusion that this is invalid. All right, so then when you're doing subtraction by addition, and remember we talked about this last class. I mean, why would you want to do subtraction by addition as opposed to just straight subtraction? Like, what's the advantage of doing subtraction by addition? Less hardware. Less hardware, exactly. Yeah, less hardware, right? Because if I can do subtraction by addition, I'm using the same hardware to do subtraction as I am for addition. Where if I did straight subtraction, I'd have a whole different hardware. Okay, so as we talked about last time, and you knew before this class, right? A minus B is the same thing as adding A to the negation of B. But how do we negate B? Take the two's complement, exactly, right? This is two's complement the verb, right? There's two's complement the noun, which is just a listing of the numbers that I gave you on that handout. But to negate, we just take the two's complement. So, you know, here's our A value, here's our B value. So we just take our A value as it is, but now we're going to add A to the negation of B, right? So to negate it, I take the two's complement. So first I invert the bits. So I have 1, 0, 1, 1. Then I add 1, 0, 1, 0, 1, 1. So that's the negation of B, and that's what I add to A. 1, 0, 0 carry 1. Sign. Okay. Now, what can we say about this result? Valid or invalid? Valid, right? Because we're adding a positive to a negative, which is always valid. And then we can convert to base 10 just to make sure. This would be 5 in base 10. What would this be? Minus what? Minus 4. So we should get plus 1, and indeed we do, right? That's plus 1. Okay. So up to this point, it's been a review of what we talked about last time, right? So any questions on this? Okay, so I'm going to turn the camera. I got a streak going again. I did it. I turned the camera my first 2 classes today, and I turned the camera last time in this section. So I'm on a streak of 4 right now. Okay, so this is the lower level structural model of lab 4. And before we talk about it, let's come up with the high level black box diagram for that structural diagram. And I've asked this a couple of times before. What is the main purpose of the high level black box diagram? What does it show us? Yeah, the main inputs and outputs. So how many inputs do we have here? 3. All right, 3. See? Outside the dash box, those are the main inputs and the main outputs. So in lab 4, you still have input A that's 4 bits and input B that's 4 bits, right? The 2 numbers that we're adding. A and B. But in addition, lab 4 has this sub input. Okay, which is just a single bit. So in lab 4, you're going to have 4 switches on your basis board for input A, 4 switches on your basis board for input B, just like you did for lab 3. But then you'll have an additional switch that's the sub switch. Okay, and we'll see what that's doing coming up soon. Okay. And then on the output side, you have your 7-bit seg and your 4-bit AN, which is short for anode, just like you did for lab 3. But there's an additional 1-bit output NIC. Okay, so you got your 7-bit seg, your 4-bit AN, and then your single-bit NIC. Okay. All right. So let's go ahead now and let's see how this circuit works. Now, right off the bat, because unless I bring this up, you know, I'll get this question like 20 some odd times, people in the room. So I just want to tell everybody right from the start, and that's when you look at this diagram, you'll notice that there's no internal signal T2, right? There's T1, T3, T4, 5, 6, and there's a 7 too. Okay. I'll explain why there's no T2, but when you put this together, if you want to change what these internal signals are called, and in fact, I would advise that you be more descriptive. Okay, like instead of calling this T1, you could call it like mux_B, right? Because it's connecting the output of this mux to the input B of this RCA. Okay. But in a little bit, I'll explain why there's T2. All right, but we're going to look at this part of the circuit first. So, A and B are going to be the two numbers that we're either adding or subtracting. And this circuit has been designed to treat those inputs as 2's complement numbers. Okay, remember that zeros and ones in of themselves are just voltage levels. It's the circuitry that gives them meaning. Okay, so this circuit is given these two numbers here the meaning of 2's complements. All right, so let's make sub equal to 0. All right, so on your basis board, whatever switch you pick to be the sub switch within your constraints file, when you have that switch down, that's going to put a 0 on that input. And that sub input is connected to the select input of this mux, so it's going to make it 0. And it's also connected to the Cin of this RCA, so it's going to make Cin equal to 0. Now, I mentioned this last class, and this is the first thing you should do today if you haven't already done it, in that you want to modify the RCA that you already have and make it all full adders, right? Because in lab 2 and also lab 3, your RCA had 3 full adders and 1 half adder. Okay, but you want to make it all full adders. And when you make it all full adders, that full adder that replaces the half adder, well, it's going to have a carry-in input. And you want to connect that carry-in input of that full adder that replaced the half adder to the carry-in input of the RCA, right? You'll have an additional input to your RCA that you can label carry-in. Okay. Now, I might not have mentioned this last time, but once you modify that RCA, you need to simulate it again, right? Because once you change something, you can't count on it working necessarily, right? I mean, just because it worked before you modified it doesn't mean it's going to work after you modify it, because maybe when you modify it, you make a mistake. Okay, so once you make this RCA all with full adders, simulate it. And I recommend that when you simulate it, use the same 10 test cases you did when it had a half adder, and add an additional 10 test cases where Cn is equal to 1. That would be the most, the most thorough testing of that RCA after you modify it. Okay, so you'll have 20 test cases when you test that modified RCA. I mean, I can't tell you how many times I've had students where, they put everything together and it's not working. And we find out it's not working because the RCA is not working any longer, because after they modified it, they never went back and checked it and made sure it was still working. Okay, so again, the proper way, the best practice when you're modeling something in Verilog is to always test the lower level modules before you test the overall. Okay, but getting back to this. Okay, so we're going to make sub equal to 0. So that's going to make this select input of this mux at 0. And you all should know how muxes work, right? Because that was in your lab 3 design. So what is the output of this mux going to equal if my select is a 0? B. Right, it's going to equal B, because B is connected right to input 0 of the mux. Right, we have B right here. What's the input 1 of this mux? Not B, right? Because see, there's an inverter connected between where the B input is and where the 1 input of the mux is. So you see right here, at the 1 input of the mux, you got not B. So if the select is 0, that's going to connect the data that's on input 0 of the mux to the output, which is B. And that data is going to go up to the B input of the RCA. Also, your A number, right, is connected right to the A input of the RCA. So now the RCA is going to add these 3 inputs. It's going to add A, B, and 0. And at the output sum, you're gonna have whatever A plus B is. Okay? So everybody agree with that? That makes sense? All right, so now, if we make sub equal to 1, that's gonna put a 1 on this select of the mux. It's also gonna put a 1 at the carry in of the RCA. So now, since the select is 1, the data on the mux input 1 is gonna be at the output. So now you'll have not B at the output of the mux. And that not B is going to be at the B input of the RCA. So now when this RCA does the addition, it's going to add A to B flipped plus 1. So what essentially is happening to B? Because it's getting flipped and 1's being added to it. That's the 2's complement. So it's being negated. So now A is being added to the negation of B. So at the output of this RCA, you're going to get A minus B. Oops, I'm running out of words. Okay, so you see that's why this input is called the sub input. When it's a 1, you're going to get A minus B. When it's a 0, you're going to get A plus B at the output of that first RCA. Now, you see the reason why T2 is no longer shown is because this diagram wasn't always like this, okay? I mean, it's been a number of years. It's probably been 5 or even maybe 7 or so years ago. But this was done a different way at one point where we had a whole separate RCA to add 1 or to add 1 after B had been inverted instead of modifying the RCA. Like we had a whole nother RCA with a half adder, like a whole nother piece of hardware. And because there was a whole nother RCA here, we needed another internal connection, and that's where T2 was. Okay, but then one of the, I think it was Dr. Benson, she modified it to this to make it a little cleaner. Okay, so T2 went away, and I never went back, or no one that I know of anyway, ever went back and renumbered the internal signals. But like I said before, I would be more descriptive anyway. And it doesn't really matter what you call these. Like I said, I brought it up because usually if I don't, people are like, oh, we're missing a T2. They think something's wrong, but everything's okay, right? Okay, so everybody good up to this point? All right, now let's look at the validity checker. Now this is a whole nother module. Okay, you're gonna have to create this from scratch, okay? So look at the inputs. It's got 3 inputs, A, B, and S. Okay, A is connected to the 3rd bit of the A input over here. And this B input is connected to the 3rd bit of this B input here, right? The 2 numbers that we're either adding or subtracting. And then S is connected to the 3rd bit of this sum output of the RCA. So first of all, can you see a reason? Like, what would be the reason we would want the 3rd bit? Remember, the 3rd bit is the most significant bit. What's the significance of the most significant bit here? Right, that's the sign bit. So we're taking the sign bit of this number, the sign bit of this number, and the sign bit of this result, right? Because that's what we need in order to determine from these rules if we have a valid result or not. Okay, and you know, the only reason we don't have lines that are actually going like from here to A and from here to B and from here up to here is just to keep the diagram not as cluttered. Okay, you'll see this a lot. This is just kind of like shorthand where you make your diagram less cluttered. You know, you don't have lines going all over the place. Okay, and you can see the output is labeled valid. So when we have a valid result, we want valid to be 1. When we have an invalid result, we want valid to be 0. So like I said, you're going to have to come up with the code that models what we want this to do. And there's at least 2 approaches to the validity checker. The 2 most common approaches is one approach is to use an if statement. Right, so remember you used an if statement for the mux. You could also use an if statement for the validity checker. Another approach that you can use for the validity checker is you could make a truth table. Right, we do 3 inputs, A, B, S. And output valid, let's say. And then because we have 3 inputs, right, 3 1-bit inputs, how many combinations do we have? How many combinations if you have 3 bits? 8, right? 2 to the 3, remember? So you're going to have 8 rows in your truth table, right? 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. And then you got to figure out, okay, what is valid equal to, right? If it's valid, it's 1 for that combination. If it's not valid, it's 0 for that combination. And then you can take that truth table, go into a K-map. And then from that K-map, you can get the reduced expression for valid, right? You would just look at where all the ones are. And then in Verilog, system log, you would just assign valid to the Boolean expression that you come up with. So, you know, this approach here, it's just like what you did the first couple of labs. Remember the first couple of labs, you would have some truth table, go into a K-map, get the reduced expression, and then you put that expression into Verilog. Okay, so inside this block could just be one Boolean expression, or you could have an if statement. I've also seen people do it with a case statement. Yeah, I've seen people, I mean, this isn't as common, but I've seen people use the concatenation, you know, joining of bits, and they join these 3 bits together, and then they use that as a variable within the sensitivity list of a case statement. Okay, so, you know, there's a number of different ways to do this. Is any way any better? No, I mean, it's usually just personal preference, but you know, how a person does it. Right? And you know, unlike, you know, when you did the mux, right, you didn't have an option. I said use an if statement. I mean, you can also use a case statement for a mux, but the reason I wanted you to use an if statement for the mux is because I was going to require that you use a case statement for the decoder, because decoders are usually case statements. You can use if statements for decoders, but they would just be like a lot of else ifs. So anyway, the only reason I made it a requirement for an if for the mux and a case statement for the decoder is to make sure you did at least one example of both. But here you have your choice, if, or do it this way, or if you wanted to use a case, you can use a case. All right, so if our result is not valid, that means this output of the validity checker would be 0. And then that output goes to the select of this mux. And it also goes to this input of this AND gate. Okay, so let's see what effect the 0 is going to have on this mux. And in fact, this should look familiar. Because where did you see something just like this? This mux that connects the data 1111 and 1110. You've seen this recently, right? It's in lab 3. And what was it doing in lab 3? Like the mux in lab 3 that looked a lot like this, what was it doing? Yeah, it was shutting off all the 7-segment displays or only lighting up one, depending on what the carry out of the RCA was, right? Because that way we would blank the displays if the result was greater than 15, right? And show the result on one display if the result was 15 or less. Well, here, same sort of thing. It's just we're controlling it with the valid bit. That if it's invalid, right? If the select is 0, it's going to take this data, all ones, and send it to the anodes and turn off all the displays, right? Because if we have an invalid result, we don't want to show anything on the display. And if we have a valid result, right, this output will be a 1. That will put a 1 on this select. And that will take this data, the 1110, and send it to the anodes, and therefore light up the furthest to the right segment so we can see the valid result. Okay. Now, when this valid output is a 0, and it puts a 0 at the input of this AND gate, and this is an AND gate, and you should be, by now, you should be familiar with the logic symbols. Like, you should be able to tell an AND gate symbol from an OR gate symbol from, you know, an exclusive OR and all that. So remember how AND gates work. If I have just 1 0 at the input of an AND gate, what am I going to get at the output? A 0, right? It only takes 1 0, because to get a 1 out, you need all the inputs to be 1. So the output of this AND gate would be a 0. And that would shut off. You can see the output of this AND gate, it's connected right to this neg output. So that would shut off that LED. So again, if it's invalid, we don't have any display on, and we don't have any LED on for neg. Okay? All right, so everybody see what's happening here with the validity check and this much. We're going to talk about up here next. Everybody's good up to this point? Okay, so now let's come back over here at the output of this first RCA. Well, if the result, you know, whether it's addition or subtraction, doesn't matter. If the result here at the sum of this first RCA, if it's positive, that means my sign bit's going to be 0. And, you know, I'll have whatever number after that. Okay. For what I'm about to talk about, the number that's after the sign bit's really not important. It could be anything. But what's important at this point is when you have a positive result, your sign bit's going to be 0. And notice the other input of this AND gate goes to the 3rd bit of T3, this internal signal. And that's connecting this sum output to the rest of the circuit that you see here. So the 3rd bit of T3, that's the same as the 3rd bit of the sum output, which is our result. Okay, so if we got a positive result, that's going to put a 0 on this AND gate. So like we said before, if you have at least 1 0 at the input of an AND gate, that's going to put a 0 at the output. And that goes whether it's valid or not, right? Because, you know, this is a 0, our result being positive. Whether it's a valid result or an invalid result, we're going to get a 0 at the output of this AND gate, right? Because it only takes 1 0 on the input of AND gate to get a 0, and that's going to turn off neg, right? Because we don't want this neg output to be a 1 unless we have a negative result. Right? So since we have a positive result, we want that to be off. Also, the output of this AND gate, it goes to the select of this mux. At this input, we have this output. See how the output S here goes right to the 0 input of this mux. So if we have this data, this result here, it's going to also be at that 0 input. Now, the 1 input of this mux goes up to the sum of this second RCA. Okay, we're going to talk about what's happening up here in just a bit. But if this select line is a 0, it's going to connect that positive result and connect it to the input of the decoder. And this decoder is the same decoder that you have for lab 3. So you don't make any modification to this decoder. Okay, you just copy it over from lab 3. And the way you design this decoder, if you have a 0101 coming into it, what is it going to display? Because when you made that decoder, it was a case statement, right? And you had 0 option, and it was going to display a what? If you have a 0 going in, you made it so the decoder is going to light up what on the 7-segment display? A 0, right? And if it's a 1, it's going to display a 1. So if you have this coming in, you made your decoder such that it's going to display what? A 5, okay? Which is the answer, right? A positive 5. You know, the neg light's going to be off, meaning it's positive. And since there's a 5 coming in here, and the way you design your decoder, it's also going to light up a 5 on your 7-segment display. Okay? So when you have a positive result, this part of the circuit has no relevance. Okay, this part of the circuit is not relevant when you have a positive result, because when you have a positive result, we're always going to choose the data that's on the zero input and feed that to the decoder. And this zero input is connected to this output where the positive number is. This part of the circuit is relevant when you have a negative result. Okay, if you have a negative result, your sign bit's going to be a 1. We'll make it 0, 1, 0. Okay, again, it's not so much important the data after the 1 for what we're talking about. What's more important is the sign here. Okay, so if we have a negative result and this sign bit is a 1, that's going to put a 1 here. And if we have a valid result, again, if we have an invalid result, it's just going to blank the displays and not light up the neg light. But if we have a negative result that's valid, we'll now have 2 1s at this AND gate. So that will give us a 1 at the output. Also, notice that there's an inverter between where this negative result is, right? The output of this sum of the RCA and the A input of this RCA. So this inverter is going to invert that negative result. So we'll have what? We'll have 0, 1, 0, 1. Right? I'm just inverting this, right? Because this is at the input of this inverter. So we'll have the flip of this bits on the output side of that inverter. And then look at this RCA. This RCA is going to take the flip version of the result, add 0 to it, and add 1 to it, which is the same as just adding 1 to it. So effectively, what's happening, if I'm flipping the bits and then adding 1, what am I doing to this result? 2's complement. I'm inverting it, right? So at the output here, we're going to have the output of our first RCA flipped, right? So the 0, 1, 0, 1 plus 1. So that's going to be 0, 1, 1, 1, 0. Right? And see, this hardware is doing what you would do manually to take the 2's complement, right? Because manually you would flip the bits and add 1. And that's what's happening at RCA2, right? The inverter is flipping the bits, and then the RCA is just adding 1 to it. So that's why we made the B input 0, because we just wanted to add 1. Okay? So that's what we're going to have at input 1 of the mux. We're going to have this 2's complement of our negative results. So now this 1 of this AND gate, right, because it's negative and valid, well, that's going to be at the select line of that mux. It's also going to light up the LED that tells us it's a negative result. And when we have the 1 at the select of this mux, it's going to put this data into our decoder, and it's going to display -6, right? Because the neg will be lit for negative, and the display will show 6. See, if we didn't have this part of the circuit, if you took sum and directly connected it to your decoder, you would have 1, 0, 1, 0 going into your decoder. And what would be displayed if you had 1, 0, 1, 0 going into your decoder? Because in your case statement, the 1, 0, 1, 0 option, what did you set the segs to light? Don't remember from lab 3? Because remember the case statement, you had 0, 1, 2, 3, 4.
There we go. It's like the letters.
Right. In fact, what letter is 1, 0, 1, 0?
Letters.
A. Right. So you see, if you had connected this sum output right to your decoder without going through any of this, for a 2's complement result of -6, your decoder would output an A, because your decoder was designed to treat these bits in hex, not 2's complement. Okay? Another way or another approach to this circuitry is you could get away with it, or do away with this and then modify your decoder to display two's complement. I mean, that's another way to do this. Okay, but we decided for you to keep this the same and introduce this because it gave us another opportunity about talking about taking two's complement and showing you how you can do it with hardware. Okay. All right, but I thought it was important to go through this with you because chances are this is not going to work the first time. Okay, you're starting to get into more complicated, more modules, more connections. The more modules, the more connections you have, the more opportunity to make errors. So it's very likely this isn't going to work the first time you try. Well, having an understanding of how it works can help you troubleshoot, right? Because let's say, you get this all together and, there's a number of test cases I'm going to give you and I'll show you coming up in a moment or so. Well, let's say, you go through the test cases and let's say all your test cases that give a positive result all work. But all the test cases that give a negative result all don't work. Well, immediately you should go right here, right? Because this is the part of the circuit that, is taken care of when you get a negative result. Right? Like we said, this part of the circuit has nothing to do with when you have a positive result. So you see, by understanding how the circuit works, it helps you troubleshoot, right? Because it can lead you to the place of the circuit where the problem is most likely at. Earlier today, I have my 8 to 11, 12 to 3. There was a student, I think in the 8 to 11, gets it all together. Every test case, the answer's off by 1. Like they're all off by just 1. So where would you immediately look at if everything's off by 1? Like what would be the first thing you would suspect might be a problem? CN, right? Because CN here, 1, CN here, 1 when it's in the sub position, right? So, that's the first thing I told him. I said, well, take a look at your elaborated design, right? The schematic that Vivato creates, and compare it and see, like, maybe this 1 isn't connected or maybe sub's not connected. Now, he never came back to me, so I don't know exactly what it was, but he was able to fix it. Let's see, I'm trying to think of another one that's come up. That's the one I remember, or those two are the ones I remember most clearly. But anyway, it helps you troubleshoot by having an understanding of what the components are doing in a circuit like this. Now, the activity is also something to help you troubleshoot, not only this class, but the remainder of this quarter and also in CPE133. And that's Dr. Benson made a video. In that video, she shows you how you can take any signal and put it on your timing diagram. Your timing diagram defaults to these main outputs and also the inputs. That's what it will show you by default. But there's a way where you can put this signal on the timing diagram. You can put this signal on the timing diagram. You can put this signal. You can put any of these signals in the timing diagram. And by putting these intermediate signals on the timing diagram, you can trace the signal as it goes through. And that way you can find where the problem first arises. Okay, so the activity is, first watch that troubleshooting video, and then I want you to demonstrate to me, you have to do it in person, demonstrate to me that you can put this T4, which is the output of the second RCA, you can put that on the timing diagram. Okay, and again, it's not due until next Thursday after the midterm. Okay, I don't think many people will get to the point where they're simming this whole thing. I imagine a few people will, but it's going to take most people, I think, longer to get this all together to test. That's why I'm giving more time till Friday of next week. Okay. Oh, I forgot to fill this in, but we answered this. This was 8. Right? 8 test cases because you have 8 rows in each table. Okay. So the next thing is, how do you model this inverter? How do you model this AND gate? and how do you connect up the data, which you've already done. Okay, well, just like in lab 3, you connect the data in the structural model. Okay, so just like what you did in lab 3 for this mux, you do the same thing for this mux. Also for this B input, dot B in parentheses, this data. Same thing here for CN, dot CN. And then in parentheses, 1 tick mark B1. Okay. The inverter you also do in the structural model where you're making the connections. Okay, the way you would model this inverter that's connected to input A of this RCA is you would just, for the RCA, when you're making the connection for the RCA, you would just put dot A and then in parentheses tilde, what is it connected to? T3. So that's going to connect this A to the inversion of T3, right? Because T3 is at the input of this inverter and then it gets inverted. So we show the inversion with the tilde. And then this AND gate, the way you take care of that AND gate, and you saw this, you may not remember, but if you look back a couple of weeks ago when we were first talking about structural modeling, and you did that activity where there was like pizza and fruit and sort. And if you go back and look, a couple of those examples, they had gates. They had like an OR gate or an exclusive OR or something. And the way that you model the gates in your structural model is with an assign statement. So you would just have for this AND gate, you would just have assign. And the output of the AND gate is T6. So you would just have assign T6 equal to, and then you would have to put the inputs T3, well, the third bit of T3 and also T7. So you put your inputs and then you just AND them together with the ampersand. Okay. So any questions up to this point? The only thing left for me to show you before you can start working is I just want to show you on Canvas a couple of things. But before I put the screen down, do you have any question about anything we've gone over? Is everything kind of making sense, hopefully?
The details, the AP and S are just the one in the original.
You're talking about this A? Yeah, this is the third bit of this A input. This is the third bit of this B input. This is the third input of the results here, right? Because in order to see if these rules are valid or not, right, I need the sign bits of what I'm adding and also what my result is. Okay. And like I said, there's a number of different ways to do it. Okay, any other questions before I pull the screen down and turn on the projector? Okay. Mm-hmm. Oh, one other thing I wanted to point out on the diagram real quick. Wake up. Notice for the RCAs, notice that the carryout output is not connected. Why is that? Why don't we care about the carryout for the RCAs? Like particularly this one here, this first one. Why don't we care? When we do an addition or subtraction like this, like right here, where's the carryout here? Like in this. We got these 5 bits here. Where's the carryout? Yeah, it's the one that's to the left of the sum bit. See this? In your result, these 4 bits, that's the sum. This is the carryout. Right? And like we said, if you get a bit to the left of the sum bit, it doesn't mean anything. Right? So that's why we don't connect the carryout of the RCA to anything, because we don't care about that bit. So again, it's just an example of sometimes you have a device with an output that you're not going to use. Okay, there's nothing that says you have to use an output. Okay, now, in Vivado, when you run the simulation for the overall, you're gonna get a warning, right? You'll get a warning to something of the effect of, the carryout's not connected. Okay, and that warning is just to let you know, hey, it's not connected in case you wanted to connect it, right? But since you know you don't want to connect it, you just ignore that warning. Okay? Okay, but on Canvas, this is the video I was referring to that Dr. Benson made about troubleshooting. So this is what you want to watch before you show me the activity, because you won't know what to show me until you watch this. And then also the test cases for that for, they are right here. Again, it's hard to see on the screen, but they're clear on Canvas. And you want to make sure that you do these test cases. Don't do, other test cases. These test cases were not picked haphazardly. They were all picked for a reason. And they do every combination of A and B, positive, negative, and also, add, subtract. And also, the values are picked such that you have one occurrence of every value, in the range of 3-bit or 4-bit RC. And then, A is the left and B is the right. Okay, don't switch them. Okay, you have to do these test cases exactly as you see them. Now, obviously, these are in base 10. And when you do your test cases in your test bench, your sim file, you can list them as base 10. But I would actually recommend you to put these all in 2's complement in your sim file. Because when you run through these test cases on the basis board, you're going to have to know the 2's complement on the basis board, right? You can't input a base 10 on switches. So if you have them in your simulation, you can just look at your simulation as you're going through the demo. And also, this is where that handout I gave you that lists all the possible values you can have for 4-bit 2's complement comes in handy, because you can use that handout when you make your test cases, and also when you demonstrate on the board. Okay. All righty. So, do you have any questions before you get started? Because that's all I have to say. So, you got the rest of the time to work on lab 4 today. Okay. And if you have questions, I'm here. Blake is here. All right.